Hi, my name is Chris Schulte, and today we're talking about lab number 4 with the topic of magnetic braking and Faraday's law. The purpose of the lab is to explore the interaction between a falling magnet and a tube of aluminum foil utilizing principles such as Faraday's law and magnetic external magnetic fields. The goal of the lab is to collect observational data of a magnet falling through a conductive tube of aluminum foil and then to model the magnet-tube interaction computationally. Finally, we were to compare the computational predictions with the observed data. Some fundamental physics principles models used in this lab include Faraday's law, which states that the induced EMF in a conducting circuit is proportional to the rate of change of magnetic flux linkage within the circuit. We also use Lenz's law, which predicts the direction of an EMF induced by a changing magnetic field through a loop or coil of wire. The EMF is directed so that if it were to cause a current to flow in a conductor in an external circuit, then that current would generate an extra magnetic field in a direction that would oppose the change in the original magnetic field. We also use the Biot-Savart law, which relates magnetic fields to the currents which are their sources. Finally, we use Newton's second and third law, which states that F equals ma, and that for every action or force, there is an equal and opposite reaction. Some equations used include that EMF equals negative n times delta phi over delta t, that the derivative of the magnetic field equals mu naught over 4 pi times ideal crossed with r hat divided by r squared, that the magnetic field equals 4 pi mu naught divided by 4 pi, and that Q times V crossed with R hat is divided by R squared. We also know that I equals V divided by R. Overview of results. The system in this lab is the bar magnet and the roll of aluminum foil, and the surroundings is the earth. Results. The average time it took for the magnet to fall through the tube, or the experimental value, was 3.6 seconds. The time derived from the computational model was 3.71 seconds. Data and analysis. The magnet mass was 0.023 kilograms, the length of the tube was 0.28 meters, the width was 0.15 meters, the inner radius was 0.0125 meters, and the average time that over the 5 trials was 3.6 seconds for the magnet to fall through the tube. Here we see our computational model. In the screenshot, we see that the dimensions and measurements of the components for this experiment. Here, this section of the code establishes the size and dipole moment of the magnet as well as the magnetic field. Here we see the calculation for the d flux divided by dt for the partly entered material. Here, we see the calculation of the magnetic field. And then here we see the calculation of the net force on the magnet as well as the magnet's velocity and position. Finally, here we see the visual model as well as the velocity versus time graph that was generated. This computational model predicted that the bar magnet would fall through the tube in 3.71 seconds. Here we see the answers to the lab questions. The computational model was red, so red must be counterclockwise and blue must be clockwise. This is based on the fact that the induced current must be in the counterclockwise direction because the North Pole was facing downwards. The dynamics of the systems that the bar magnet was flipped would cause the induced current to switch directions. Conversely, the change of flux would be constant, therefore motion would be the same. The computational model is likely more accurate as it does not contain human error or face any resistive forces like air resistance. The shape of the velocity versus time plot tells us that we will eventually reach a terminal velocity. Conclusions. In this lab, we see the connection between Faraday's law, Lenz's law, the Biot-Savart law, as well as Newton's second and third law when predicting the motion of the magnet. Assumptions and error analysis. In this lab, we assumed error resistance was negligible, and we did see that there are some possibilities for error, such as when utilizing the meter stick to measure length, inner radius, and width. We also knew that there could be inaccuracies in recording the magnet falling, and therefore the timing of the magnet when playing back the frames of the video. Since all the above are assumptions and idealizations made, there is likely a slight error in the calculated and observed values despite controlling as many variables as possible and being precise in measurements. What if? What if the resistivity of the conductor were to be reduced as close as possible to zero? How would the dynamics of the falling magnet change? The current would be increased, therefore causing the magnet to move slower through the tube. The behavior of the magnet given in this scenario aligns with that predicted by Ohm's law. What if holes or slots were cut into the tube? How would this affect the ring currents in your model? If these slots or holes were cut into the tube, there would be less rings. This means that there would also be less induced current and less magnetic force on the magnet, causing it to fall faster. Thank you.